Okay, before the break, we learn a few calculation. First, reduction of co-reduction. This one is more on thickness. Means this one is the thickness. You make comparison of the original thickness. Okay, so you know that this is positive value. So when you reduce it, you must take the original minus the final, because the final thickness is smaller value. So this is how you memorize. Then for the stress and strain, you take force divided by area. Important is you have to identify the direction of the force. It must be perpendicular to the area. The force direction and the area must be 90 degrees. Then force divided by area, you get Newton over meter square or Pascal. Remember on the unit SI, change all the unit into unit SI. Then tensile strain is a deformation parameter. It's a ratio of original to the changes. Then another one is the Hooke's law. Hooke's law is stress equal to capital E and strain. Okay, stress equal to capital E strain, and the capital E is called modulus of Young. Okay.
The E and the mu is the same moment.
The small one.
Small one.
Okay, the small one is strain. It's a half circle with a small dash at the center. You can write like a small E lah. You can write a small E, but not the round E. Not the round E.
Like a capital E, but very small lah.
Yeah.
Okay. But the symbol and mu is different thing, right?
Yeah. Okay. So this is how you see in your test. So you'll see the sample like what you see in your experiment, right? So this is called dog bone sample. So you have a pure aluminium. White is given 12.7. So, okay. And then 1.06 thickness. And 203 mm long. Okay. That has a gauge marking 2 inch or 15.8. This one. So that's why in your experiment, I mentioned you need to label the 2 dot, the 3 dot there. Right? So the 3 dot, the two dot actually is the gauge length. Okay, so the gauge marking is when it's under stress, there's a change of the length from 2 inch to 2.65 inch, or you change in the unit SI from 50.8 mm to 67.31 mm apart. Calculate the normal engineering strain and percentage of strain in that sample. What is the equation for strain? Strain is a deformation, right? You take the changes of length divided by the original length. So what is the value of the ratio?
2.65 minus 2 over 2.
Wrong.
Do we take the whole thing?
What is the unit SI?
Oh, we have to convert from inches to meters.
Inch and mm is different. So you can do conversion 0.65 to mm, or you can take the 67.31 minus 50.8 divided by 50.8. It asks you strain, not stress. Okay. So strain is a change of deformation. So in this case, the length is changing. All right. And the question also didn't mention about area. So I mentioned about the length. So you do calculation of length. The answer will be 0.235 The question asks you to do percentage of strain. So you multiply by 100 is 32.5%.
So you get marks for writing the formula also.
Which one?
Formula like
General formula.
yeah,
Yes, of course. You must write this general equation first, then you only substitute. Okay? So if you straight away substitute, you will lose mark for general equation. Okay. So this is 1 mark, this is 1 to 2 mark, this is 2 mark. So it's about 5 marks. So you straight away you substitute like this, you give me this, get 3 marks. Okay, you miss out the general equation. You don't show your understanding on how you get your answer, right? So you always have practice to write general equation. Right. And important, don't leave your answer blank, because your lecturer will try to help you so that you don't fail. So don't leave your answer blank. You blank, I cannot help you. Okay. Next, we learn about Poisson ratio. A Poisson ratio is a deformation, but it's in 3-dimensional. Poisson ratio, when you pull a metals, the shape will change, right? From the dot one is the original shape. If you pull at both ends, it will become longer and longer. The diameter, the length also will change, right? So you have a Z direction, X direction, and Y direction. Right? So what is Poisson ratio? Poisson ratio also a ratio. You do not have any unit. So tensile stress, if you see the word tensile means the arrow is pointing outward. So in this case, pointing in the Z direction. So it will create positive tensile strain. Agree? Positive tensile strain means there's a changes in the length in Z direction. You pull, the length will change. Okay. So again, before I go forward, remember the equation you learn is all tensile, but when the question can to change to compression, it's a reverse. You compress things. For example, if you compress things, the length become shorter. You get a negative value. Okay. So back to these slides. So lateral normal compressive strength. Why on the Z you get tensile? Why on the X and Y you get compressive? Why did you see the word compressive? You go inside. You go inside. It's like you're pressing the side. Go inside. So you go inside, the change is negative. The strain in X direction becomes shorter. From this one to this one, becomes shorter. So you get negative. So here also same. Yeah. Now how to get the strain again? Is you take the changes of, you take the final length minus initial length divided by initial length. Final minus initial. Right? Okay. So if you see the question mentioned isotropic, isotropic means the changes in X and Y will be the same. Isotropic means same direction. Iso means same. Iso means same. Tropic means same behavior. So if you have same behavior along the side, then the strain for X and Y will be same. The magnitude will be the same. Okay. So this ratio is called Poisson ratio. It's Greek. It's how you write. It's like that. If you want quick, you can write V, but slanted a bit, right? You can write V also if you want, right? So it's a Poisson ratio. You take strain in lateral divided by strain in longitudinal. What I mean by longitudinal? This is longitudinal, long. Okay. It's a plane, lateral. So you have two lateral strain in three-dimensional object with its x and y. X and y. Okay. So you have x and y. So sometimes the question will say you are having an isotropic behavior. It just gives you one side of the changes of the side dimension. You can calculate another one with this. You are given x, you can find y. If you see the question give you isotropic behavior. Okay. All right. So far it's quite direct. Nothing complex here. Only don't confuse with the top and bottom equation. The top one is lateral, below one is longitudinal. Okay, top one is lateral, below one is longitudinal. I've seen mistakes where students confuse these two. Okay. All right. Now another new equation you need to memorize. This equation won't be given. You can link all these position ratio. One more. Position ratio equal to lat divided by long, but this is strain, right? So again, if you have metals in the longitudinal, usually you will get negative sign for the position ratio. Okay. Positive and negative depends on how and where you refer to. Positive when you usually is a longitudinal side. Okay. Position ratio is negative for metals, normally metals. Then you memorize modulus Young equal to 2G1 plus position ratio. Okay, what is G? G is a parameter that link modulus Young and the position ratio. There is a table. There's a table. For example, this one. So you're given a few material. You're given elasticity, which is E. Shear modulus is the G. Position ratio is this one. Okay. So normally you see this kind of table in the question paper. So again, you memorize this field. You write this one. 1 mark, 1 mark, 1 mark, 1 mark, 1 mark. So 4 free marks here already. Okay. So this another example. So when you see table, look carefully. Don't use the wrong column. This one is PSI. This one PSI. Use the unit SI, gigapascal. Giga is 10 power 9. Okay. Okay. So then this is another behavior. When you plot, you do experiment, you will see temperature and the modulus E, the E, capital E, then temperature, Celsius and Fahrenheit. This one on the top and the right is this one is unit, imperial unit. Okay. Okay. Just now we learned about the normal direction. Now we go into shear stress. Again, if you see the word shear, remember the direction. Shear, the force is parallel to the direction. Okay. You learn static, you learn a lot of trigonometry, right? So let's say you are given a force with a degree. You know that the force can split into two directions, right? So this kind of force with the angle one, it can give you normal force and shear force. Normal force is 90-degree one. Shear force is parallel to the area one. So be careful when you have an angle. Okay, so this is what I mentioned. So when you see the word shear stress is always with the force and the area parallel. So you see 4 arrows here. Blue color This one we label as S for your convenience, but usually when it comes to your assessment, we will just use F, force. So force parallel to the area is a shear force. Okay, and if you have shear force like this, the object will deform in a certain area, certain degree, like we see on the screen here, right? Okay. Shear stress. Shear stress. The stress word means force divided by area. Only you need to be careful on the direction and the area involved in that force. Okay, it's a couple. Huh? So shear force is the one that on parallel to the surface. So area, right? Area is the one that linked with the force. Same. That's why shear stress have the same unit, but the way you write shear stress is like a Latin word, or I don't know whether Tamil got this kind of symbol, I don't know. Okay, or you can write a T with the hook, umbrella, something. So, or you don't know how to write this one, you just write shear stress. Stress equal what? Okay. Same, the unit is Newton over meter square, shear stress. Okay. Then it's called shear strain. Another one, shear strain and shear stress. Shear strain, you take A divided by H. Shear strain is the angle or the degree of changes when you push a cake on the top, or jelly, you're going to deform, right? You put on the jelly, right? So you learn about trigonometry, right? Trigonometry, you have three relationship, right? So this one give you what kind of trigonometry equation? Tangent, cos, or sine? Yeah. It give you shear strain. Shear strain equal to A divided by H. Is the triangular here? The angle is here. So it's tangent. So shear strain also means tangent. So if you're given an angle, you can find your shear strain. It's a hidden information. If the question gives you tangent something, give you an angle, like it tell you the jelly block or the metals deform at a certain degree. It means like this. Okay, so also means tangent. Okay, so it gives you another relationship between the G, the shear coefficient just now in the table. Okay, the shear strain, the hooks, you link with the shear strain, which is shear stress equal to coefficient and the strain, same. Just now, stress equal to capital E. Another one is the hook equal to G gamma. Okay, this is important equation for this chapter, chapter 6, very important. Okay. Right. G elastic modulus. Okay, let's apply what we learned. A piece of copper originally have a certain length, right? And then you have a stress. It gives you a tensile stress, so and so. If the deformation is elastic, what will the resultant elongation? Oh, sorry, this one you should be referring to the table. There's a table. Okay. So you need to pull what you learned in the first session, stress, strain, and then it asks you resultant elongation. So here you need the modulus Young. How you know you need the modulus elasticity? The keyword in the question will mention elastic. If you see the word elastic, normally this equation or this equation, this equation, this equation. Okay. So you pull out the Hooke's law, you substitute the definition of stress, substitute the definition of strain, okay, which is I show on the slide here. All right. So it tells you tensile stress, right? So you don't need to change this one to force divided area. This is stress. Okay. Then it tells you the elongation. You want to find this one, right? So rearrange the equation. Put this one here, put this one here. Yeah. So in engineering dynamics, we expect you to use general equation first, then only you substitute. Yeah. So again, you need a table to solve this one. Okay. So this one, you're given a copper. You look at the question. Normally, when you see a type of metals, quickly go and flip to the this kind of table, and then copy all the value for your calculation. So copper, your modulus elasticity is 110. Unit is what? Gigapascal. You have shear modulus G, which is 46 gigapascal. Portion ratio is 0.34. It depends on what kind of calculation you need. Basically, it's all these 5 or 6 equations that run on the whiteboard here. You just substitute, and then you solve the equation. Okay? Get the concept, huh? You don't need to memorize all these values, but you understand the steps of how we're going to solve this question. Okay? You substitute. Remember the unit SI and the giga, mega, you convert to 10 power something, that one. Okay. Then you cancel lah. Okay. So the deformation here is in 0.77 mm. You can write in meter. Right. So if the question didn't mention you need to put in what, usually you put in the unit SI. How many meter? Okay. Okay. Example 5, no issue, right? Very direct, huh? Example 6. So you have a tensile stress. A tensile stress applied along a long axis of the cylindrical brass rod, like what you did in your experiment. Okay, it gives you tensile stress. So you, on the object, you draw tensile stress. Okay. Have a diameter, DO, you're given. Determine magnitude of the load required. In this case, it asks you to find the force to produce a change in diameter from DO to DI. Second, this one also given. If the deformation is entirely elastic, you see the word elastic, it means you need to pull Hooke's law into your equation. Stress equal to modulus Young strain, or the shear stress equal to G shear strain. Okay, it depends on what question I want to ask you. Then recall definition of stress and strain. This is force divided. This one is delta L divided by L, or area. Okay. Okay. So you draw the behavior of the rod. Okay. You draw the behavior of the rod, and it tells you to find the magnitude of the load. So it will behave like that when you pull a brass. So the change, the elongation, the length will be changed, but there will be a change of diameter, which is the strain is changing. Okay. Rest you read, huh? So I'm showing you a calculation for the strain. So this is x direction, z direction. X direction was string, right? When you pull, the x direction was from the blue color into a red color. Diameter blue will change to red color, will become smaller. So delta D divided by D will be negative sign.
So they already gave delta T in the question, right? 2.5.
Yes. Yes.
So we have two determinants.
Only careless mistake is over here. You miss out the negative sign if you are not careful. Okay, yeah?
So whenever it's compression, we have to put the
Compression positive. You become bigger.
Oh, no, I mean, sorry, the
Tensile, yes. Tensile will be thinner, but compression will become fatter. Compression, you get positive sign. Okay, so just be careful on the positive and negative sign. Okay, the rest is unit SI, and you cancel out each other in the calculation. So the first calculation, the strain changes in x direction will be negative 2.5, 10 power negative 4. Okay, in this case it's rod. The earlier example is a square one, the square cross section. So be careful on the question. All right. Now then you go to the table. This is brass. So brass, you have the value that you need. Okay. So the position ratio for brass equal to lateral divided by longitudinal. Position ratio equal to lateral divided by longitudinal. But you take strain, right? So minus strain in x divided by strain in z direction. You have a negative sign, positive value. Negative, you cancel the negative. Okay, you substitute the value. You, at the end, elongation in z will be positive value, 7.35, 10 power negative 4. Okay, then recall the definition of your strain, longitudinal strain. Okay, so you have strain in x, strain in z, and you call out the Hooke's law. Okay, the Hooke's law, which is the E. Right. Put out Hooke's law and then refer to the table again. Substitute, you get the value of the stress. Same, you can apply with other methods, which is stress equal to force divided by area. So you have the stress in z direction. You z equal to force divided by area. You rewrite. You pull this one to the right, to the left. Stress you already calculated just now. Stress in z 71 megapascal, 10 power 6. Pi. Then pi, this one is diameter. Pi d square. Okay. Press calculator, your z, your F equal to 5,600 Newton or 5.6 kilonewton. Make sense? Make sense, huh? Okay. We have lab session this coming Wednesday, 10 to 12 p.m. Go to block E, M20, yeah, the one that beside Fab Lab. I'm going to use microscope and this one. Okay. Those missed the last lab one, go to the M11 on 4th October, means another Wednesday. You need to go and do the same, repeat the same experiment again. Okay? Right. Okay. Right, with this, we stop here. We continue this afternoon.